All right, guys. Now, in our last tutorial or our previous video, we looked at dimensional analysis, and I did mention that these three are the most important fundamental quantities you must take note of. These ones are also okay, but sometimes they vary. For instance, electric current, some textbooks may use I for the dimension. All right, this one may use K for the dimension. All right, but pay attention to these first three. All right, length, mass, and time. So capital L, capital M, and capital T. Okay, question number 14. The values of x, y, and z, respectively, in the expression this for the universal gravitational constant G. Okay, so you remember Newton's law of universal gravitation. F is equal to, you have capital G, m1, m2 over r squared, right? Okay, so if we make G the subject, we have that G is equal to F R squared. Like we are doing cross multiplication, all right? Over M1, M2, M2. Okay, so that means the unit will be force is Newton. Let's start with Newton. We'll further break it down. And then we have R is meter squared. Okay, and then mass is kg squared, right? Okay, but we also know that Newton force is kilogram meters per second squared. Do you remember? All right, so still times m squared over kg squared, so that this kg will take care of one down here, so that we will have m squared, yes, like this, m cube rather. Okay, sorry, m cube, okay, per second squared over kg. All right, okay, so I can rewrite it like this: per kg m cube per second squared, like this. All right, so once you get the unit, it becomes very easy to get the dimension, right? So I know that the dimension for kg is capital M, okay, minus 1. And then I have what? Capital L raised to power 3 and capital T raised to power negative 2. Okay, so this is what we've got. That means x, y, and z will be minus 1, 3, and minus 2. So which option? Option B is the correct option. All right, so question number 15. Which of the following quantities are dimensionally independent? That means they are unitless. All right. Once a quantity does not have a unit, it means it doesn't have dimension. So let's check the options. I, we have dielectric constant, so K is so permittivity of the material over permittivity of free space. All right, but their unit is farad per meter, farad per meter, so they both cancel. So this guy is unitless, hence dimensionless. Is that okay? All right, we check momentum. We know momentum has a unit, therefore it must have dimension. So momentum is mass times velocity. You remember? So kg meters per second. All right, so this one has dimension. What about efficiency? Efficiency is mechanical advantage over velocity ratio times 100 over 1. Do you remember? Or work output over work input times 100 over 1. All right. So whether you're referring to this or this, Efficiency has no unit. Mechanical advantage has no unit. Velocity ratio has no unit. That means efficiency does not have any unit. Hence, dimensionally independent. So if you are considering this one, work here is joule, work down is also joule. So joule will cancel joule. All right, so we come to refractive index. Refractive index, you remember we can use velocity in air over velocity. For instance, let's say we are considering air versus glass, all right? Or wavelength in air, wavelength in glass. You remember the popular one, sine of angle of incidence in the less dense medium over sine of angle of refraction, okay, in the denser medium. So whichever one you like, you discover that the unit here will cancel the unit here. So this guy is unitless. All right, so the correct option, so if we take away momentum, we'll be left with I. So D, I, and IV. So D is the correct option. Okay, question number 16. Now, they are just asking us to find the dimension for force, all right? So once you know the dimension for force, it becomes easier for you. So force is mass times acceleration, you remember? And the unit is kg meters per second squared, right? That means the dimension will be what? Capital M, capital L, and then S raised to power negative 2. Sorry, T. What am I doing? Like this. So this one is 1, this one is 1. So X, Y, and Z will be 1, 1, and minus 2. Okay, so which option is the correct one? B as well. All right, so finally, let's look at this guy together. Question number 17. The dimension for electromotive force. Now, I know that EMF is equivalent to potential difference, right? Sometimes we bring in the dichotomy by putting terminal here. We say terminal potential difference, all right? This is the potential difference across the terminals of a battery when in an open circuit, right? While this one is when in a closed circuit. So the two of them share the same SI unit, which is volts. And volts or potential difference is work done in moving a unit charge from one point to the other in an electric field. Do you remember? Okay, so work done over charge. But I know that work done is force times distance. And I know that charge is current times time. Do you remember? So if force is, you remember, kilogram meters per second squared times, and then distance is meters, current is ampere, and time is second. So that means the unit will be kg meter squared per second cube, and then per ampere. All right, so you look at the options. Okay, this is the unit. So the dimension will now be what? The dimension will be kg is capital M, L squared, T raised to power minus 3. And then the dimension for current can either be A or I. So I can change this to I like this. Okay, so which option is the correct option? I think it's this guy. No, not this one, sorry. It's A. A is the correct option, right? So because this is 1, 1, 2, minus 3, minus 1. So 1, yeah, so A is the correct option.